Well, I'm Victoria Stodden. I'm an assistant professor in the statistics department here at Columbia, and I'm going to moderate today's panel. What we're doing is, I think, an exceptionally important topic for people to be aware of and people to be discussing that's changing how we disseminate much of our research output as academics. The panel is called The Challenge of Communicating Computational Research, and I'm told this is the final event in the Research Without Borders Speaker Series for this academic year, and it's sponsored by Columbia's Scholarly Communication Program and the Augustus C. Long Health Sciences Library. So what we'll do is we have three speakers, and today's format is I will introduce the speakers and a brief touch on what they'll be talking about. Then the speakers will go ahead and talk, and then what I'll do is open the floor to questions. So if you have pressing questions on any of the earlier talks, just sort of make a note and keep them in mind until we get to the end of the three talks, and then what I'll do is open the floor. There's a mic, I think, in the middle of the room. Please use the mic as you talk, because then people who are watching this on the webcast and in future can hear your question. So I'll introduce the speakers. First of all, we're very lucky to have all of them here. Our first speaker is Neil Chu Hong. He's coming from Scotland. He's the director of the Software Sustainability Institute. He's responsible for representing the Institute and the interests of UK researchers at the national and international level. Within the organization, he oversees operation, leads policy development, develops and manages collaboration, and acts as a principal liaison with stakeholders. Neil's worked with researchers from across the UK and internationally to address barriers to the use of e-infrastructure in the research domains such as biosciences, chemistry, digital humanities, earth systems modeling, medicine, and social sciences. I'm very much looking forward to hearing his comments. He'll be talking about very concrete examples that the Software Sustainability Institute has taken on. Loosely, he's titling his talk Communicating Trust and Enabling Criticism, and what is the role of software in enabling proper digital research to be done. This is still an open question, and what he'll do is especially touch on issues around complexity of systems, particularly these software systems, and how that interacts with the appropriate communication of digital scientific research. Matthew Jockers, our second speaker, he is an assistant professor in English at the University of Nebraska-Lincoln. Prior to his position at Nebraska, he was a lecturer and the embedded academic technology specialist in the Department of English at Stanford University. When he was at Stanford, he co-founded and directed the Stanford Literary Lab. His research and teaching are focused on computational text analysis, specifically an approach he calls macroanalysis, and he has a new book titled Macroanalysis: Digital Methods in Literary History. The title of Matt's talk is Moby Dick is God and Other Things Your Computer Doesn't Know, which deals with skepticism in the humanities around digital methods for research. Many times this discussion around dissemination of computational research and its challenges has a tendency to focus on traditional scientific research and how this is becoming more computational. That's, of course, an important part of the discussion. Equally as important is how new fields such as humanity, or new areas such as humanities, are uptaking these digital research methods and doing computational science themselves. So it's very exciting to have Matt here. Our final speaker is Dan Ellis, who's associate professor in the electrical engineering department here at Columbia. His laboratory for recognition and organization of speech and audio, LabRosa it's called, is concerned with all aspects of extracting high-level information from audio, including speech recognition, music description, and environmental sound processing. He also runs the auditory email list with 1,700 worldwide researchers in perception and cognition of sound. What Dan is planning to do, this is my understanding, is use examples from his lab to describe and elucidate 5 modalities that we should be thinking about for communicating new scholarly digital objects. And with that, I'll turn the floor over to Neil. Each speaker will speak for about 15 to 20 minutes.
Thank you very much, Victoria, and thank you very much to Columbia for inviting me to speak today. So, as Victoria mentioned, what I'm going to be trying to talk about is this idea that we've been looking at as part of the Software Sustainability Institute around how software has a role to play in communicating computational research. So the Software Sustainability Institute is a UK facility which is really about cultivating world-class research through software. So what we do is we work in collaboration with different university researchers, different research groups who are either using or developing software that is the bedrock of their research. So this includes things like simulation and modeling, data analysis, or the sort of steering of equipment and infrastructure. And really what we've been going on to do is assess the different aspects that lead from this kind of direct work with different groups. So I'm going to give one specific example in my talk, but I think it can be related to many of the different groups that we work with from across the humanities, social sciences, and sciences. And really what we're talking about here is the idea of better software for better research. So what I'm going to do in the remainder of my introduction is look at what this means and what we've been finding out from the groups that we've been working with. So I'm going to start by the slightly controversial view that if you cannot be critical, you cannot be a good researcher. So I believe that research is very much based on the idea of intellectual debate. So the ability to observe, to assess and criticize one another's work. So as researchers, it's in our best interests, and it's in the interests of the research community as a whole, to understand how we can be more open and transparent about the work that we do. Because if you don't have the ability to criticize, you also don't have the ability to build on the work of others. So the question really is, in terms of software, what does this mean? And we now have software which is coming into almost all aspects of research. In particular, where we see the role of software is very often as a black box, and that can cause problems. So the issue we have now is that with all of this software coming about, we have very complex systems being modeled. So this picture here, if you can see it, is an example of aerosol flow. So all of the things that we're releasing into the atmosphere, the small particles, and the way that they drift across the continents. And understanding and modeling the way that these chemicals move around the atmosphere is important for understanding the effects of things such as acid rain, the effects of climate change, and so on. What's really interesting is that this is one simulation, and where we're moving to now is coupling many simulations together. So seeing how different systems interact, exchanging data between them. And this means that the complexity of the systems themselves grows. So what we have now is we may have people who understand the research in one area, working with someone else who understands research on another model, and trying to make the two work together. And this is starting to become more and more interdisciplinary. So we see the economic effects of aerosol migration, we see the social effects. Does the fact that you're sitting in the northwestern US mean, for instance, that the average level of intelligence drops because of pollution? All of these questions are ones that may be coming up in the future. And the issue there is that the software that's underpinning this is always growing. And what we end up with is a whole set of software which we are taking on trust. So what we're doing is we're creating lots and lots of these black boxes whereby we assume that only a specialist can understand what's within them. And this is a problem because it's basically stifling the criticism. It's not enabling us to form a proper relationship of trust with the people who are doing the work on the software, the people who are doing the work on the research, and the people who are reinterpreting the results. So I'm going to give you one particular example from the work that we're doing with the University of Bristol. And this is interesting because it has an impact for everyone in this room. So I'm going to show you a little animation here, and you have to guess what it is. So what we see here is this little jiggling thing happening. There's a molecule in the middle, and all of a sudden, the molecule gets ejected. Does anyone have any ideas what this is? Okay. So this is an example of what happens when a antiviral agent, in this case Tamiflu, reaches a Tamiflu-resistant influenza virus. So what we're seeing here is a simulation of the antiviral agent being ejected from the system. And it's the reason why some antiviral agents like Tamiflu are becoming less and less useful. And what we're looking at here is really what causes this sort of reaction. And in this case, the belief is that it's to do with the way that different parts of the molecule, the red and the blue, react in the presence of water. So it's a water swap problem. And this is something which has been successfully simulated, and we're now at the point where the length of time that we can simulate this process for is long enough that we can see these sorts of things happening. So about 3 years ago, we would only have been able to simulate for about 1/10 of this time, and all you see is the molecule jiggling around in the center. Now that we're able to do this over a longer period, we can see the ejection mechanism. And so this is posited as the reason why these drugs are starting to lose their efficacy. So the question is really, how can I trust this code? So this is a piece of code from this simulation. I don't expect you to be able to read it, but it basically sets up a whole set of interactions, and it is the main routine that's used to run the simulation and set up the parameters. So how can I, as a scientist, a researcher, trust what's going on in this code? Well, I believe that from the work that we've been doing, it falls into 4 different categories. One is openness. The very fact that I'm able to show you this piece of code, which has been developed by researchers at the University of Bristol, is the first step. I am able to look at this code, understand perhaps what it means, but certainly peer into all of the different nooks and crannies. And this is where, in the past, there have been issues when we've looked at things such as the ClimateGate affair with the UEA. One of the things that came up was that because the codes were closed, people could not find out whether there were areas of uncertainty and doubt. The second one is review. So one of the things I know about this code is that it's being reviewed by other scientists in the field. So I trust it more because what we have is peer review, and peer review is an important part of science. Third one is tests. So I know there are tests here, partly because I'm part of the group that's trying to put them in. So what we have here is the ability to assess small individual parts and check whether they're working, understand whether the system as a whole is providing the results that we would expect. And the last one, the 4th case, is automation. And this is the one which a lot of people forget about. So in this case, the simulation that I showed you was deterministic. If we started with the same random seed, the parameters that we choose to start off the simulation, it will always run the same way and produce the same results. What we have, though, is the ability to run with many different random seeds and create an ensemble of simulations that together allow us to identify the behavior. So with those 4 things, the openness, the review, the test, and automation, I believe a little bit more that the code that's represented here is doing what it should be doing. So there's this question. It's basically, how do we increase the amount of information on software without drowning in it and therefore increasing the trust? And the question that I often get asked is, but it's so much extra work, so why should I have to do it? Or does anyone really use this? And that's really what I'm going to try and push back against in the second part. So a bioinformatician called Titus Brown had a brilliant blog post earlier this year called The Ladder of Academic Software Not Suck. So he said, basically, that academic software should not suck. And what did he mean by this? Basically, he meant that we should be treating academic software in the same way that we're treating other research outputs. When we're publishing something, we should be making the software available so that people can see, but we should be going further than that. We should be making the software available so that it can be used in other people's pipelines, in this case, so in other people's work. And we should be making things available so that it can be reused by others to improve the efficiency and accuracy of our research. So he posited this ladder, and he has things such as downloadable, installable, runnable, and being able to replicate the publication's results, all as prerequisites for publishing. And if we ask ourselves really carefully whether or not we include things such as a link to the software that we may have used when we publish a paper or a book chapter, we probably have to hold our hands to our hearts and say, not always. So we're not even at that first stage of his ladder. And what we'd really like to be able to do is go all the way down, because, again, his suggestion is this ladder is the minimum required set of steps to do research. There's a whole set of steps beyond this, which is really about building on this and creating better research. So similarly, what we've been doing is we've been looking at the different projects that we've been working on and trying to assess whether there are common properties about what makes research software more reusable. And what we've tried to posit is this idea of 5 stars, a way of being able to make a quicker judgment, if you're not from the area, of whether or not software is reusable and can be trusted. And this is similar to Tim Berners-Lee with his 5 stars of linked data, or David Schotten with his 5 stars of linked journals. It's designed to be a way of comparing things, not to be an absolute reckoner of whether something is good or bad. And so if you're interested in this, please ask me questions about this. I think the main thing that I found from this work, which is potentially controversial, is that the quality, the robustness of the software is not necessarily one of these 5 points. It's more about the openness, the extensibility, whether there's accurate information, and whether or not there is a community around it that are more important than the traditional notions of industrial high-quality metrics. So, having said all this, isn't sharing scary? So, is it the case that what we are faced with is that we're afraid of what happens when we share too widely? And so here I'm going to introduce the case of Jeffrey Chang, who some of you may have heard of, who was forced to retract a number of high-profile science papers because of a bug in one of his internal analysis software routines. So he'd published the papers. As the research went on, basically there was an identification that there might be something wrong in the way that he was doing his research, and after the identification of the error, he was forced to retract these 4 papers from Science. So you might think this is a bad thing, and it's often used as an example why it's bad to share. I argue that it's exactly the opposite. So what we have here is someone who didn't share and was caught out, but actually, afterwards, has continued to go on and publish, because it wasn't his research that was bad, it was that he had an error in his calculations, and everyone gets errors in their calculations. The problem was he didn't catch the error in his calculations before he published, and neither did anyone else. If he'd opened up his software, there might have been a chance that that error was caught earlier, and it hasn't, in the end, harmed the fundamentals of his research, apart from the fact that he is now the #1 hit if you type in scientific retractions on Google. So there is a possibility that this could have been avoided if he'd shared his code. And the other thing is, younger researchers often ask, won't this just mean that I get overlooked? And I say again, you should look to Oscar Wilde for your inspiration, because really as a young researcher, not sharing is just your it's just your ticket to academic anonymity. What we're seeing increasingly is that the ability to criticize, the ability to review, is your way forward in your academic career, and it's not getting any easier. If you look at the recent article by The Atlantic looking at the academic progression from PhD to professorship, you need to do everything in your power to make yourself visible and to create a profile. What we see happening with things such as signed reviews is starting to go along that way, because you can start getting credit for the work you do in the criticism as well as the original research. So that, along with other pieces of work, for instance, Heather Piwawa's work on showing why open data makes you more citable, is exciting. it's something that basically means that there are many more ways as a young researcher to forge an academic profile for yourself. So sharing is really something which we should be doing rather than being scared about doing. So I'm going to plug now here one of the things that we're doing at the SSI to try and help this, which is the Journal of Open Research Software, where what we're doing is trying to provide ways in which people can share the knowledge about how to reuse their software. So this is a journal which encourages people to publish pieces of software that they've developed, and it's assessed not on the quality of their software, but it's assessed on their ability to describe its potential for reuse. So what we're talking about here is understanding whether or not someone else can approach it, not necessarily whether or not this is the best tested, best commented piece of software. Because I think what we have to do is encourage more people to publish. And one of the things that we put in their way is the barrier of thinking that everything must be perfect rather than just useful. So finally, I'd just like to say one last thing that's coming up, and it was made evident to me at a recent crossover event that I was at called the Salon Project, which is running in the UK, which is a really great event. You go along to a theatre, you get dressed up in a set of costumes that mimic the Parisian salons of the early 20th century, and you get a number of speakers from different universities to talk on different topics. And the one that I went to recently had a speaker from the IT surveillance community talking about the worries that we have about everyone's life being captured, that the data that we have, the personal information, is increasingly at risk. And so being part of this audience, which was mostly sort of 30, 40, 50, 60, 70-year-olds, I was intrigued by the question that came up from someone who was a teenager who simply said, why is there a social stigma attached with sharing? So I ask you that question. Will the stigma of sharing disappear? I certainly believe it will. And in that case, what happens is that we have a whole set of people who by default want to share, and they only get it beaten out of them by the time they talk to their supervisors. So that's my introduction. I'd like to leave you with this thought that communication isn't just about questions and answers, it's about sharing knowledge, and give a shout out for this little video from one of your competitors in New York at NYU. Thank you.
Well, thank you, Neil, and we'll switch over to Matt.
Well, I'm tempted to just trash my talk and ask questions of Neil instead, but that was very good, stimulating discussion. I think particularly as someone who's a humanist coming at this from a little bit different world. Well, I'll start with a little story that will take us back to the 90s when my wife and I invited some friends over for Thanksgiving dinner. And one of the friends was a grad student in English, and the other was a scientist, an outsider. And things eventually, though, as they do, came around to a discussion of literature. And there was controversy when we came to discuss the critical enterprise and what it means to engage in literary research. And the lone scientist in the group eventually asserted that the methodology employed by literary scholars is subjective and highly anecdotal and produces very little in terms of verifiable results and much in the way of unsupported speculation. Now, this takes us back a little while, and I recall rising to that challenge and asserting that the literary methodology was in fact no different from the scientific one. And I argued that scholars of literature, at least the kind of idealistic ones I imagine myself becoming, were like their counterparts in the sciences, seeking to uncover evidence and discover meaning, and perhaps even some truth. And then I dug even deeper and argued that literary scholars employ the same methods of investigation as scientists. We form a hypothesis about a literary work, and then we engage in a process of gathering evidence to test that hypothesis. Well, after a good many years, it's not such an embarrassing story anymore. And I should say I'm not completely convinced that the methods employed in literary studies are really exactly the same as those employed in the sciences, but I do remain convinced that there are a good many methods worth sharing, and that the similarities between these methods exist in concrete ways and not simply as analogous practices, which often is how they get expressed. But as a humanist who computes, I'm a very odd bird. I happen to enjoy reading and teaching James Joyce as much as coding and programming in R. And when I can join the two, then I go to my special place. To most of my literary scholar colleagues, however, I'm an aberration, living evidence that somewhere between high school and a PhD in literature, somebody dropped the ball. And I think, perhaps as a result, that it's fair to say that I spend just about every day working to communicate my computational research. And even though I run in a crowd that's called the digital humanities crowd, it's ultimately the literary scholars that I'm interested in aiming my work towards. And when I'm communicating my research, therefore, I'm almost always beginning with the assumption that my target audience has little or no technical or statistical background. And in practical terms, that means that I often have to devise analogies and metaphors to help explain complex algorithmic processes. And one of these about which I'm particularly proud is something that I call the LDA buffet, LDA being latent Dirichlet allocation, or what's more commonly called topic modeling. When I was working on my book, I was agonizing over how I was going to describe latent Dirichlet allocation to my target audience of literary scholars. All the technical papers use equations and plate notation, and folks, this is not in our PhD training. I couldn't use either of these things, although I could reference those articles for the hardcore folks. So instead, I dreamt up a little story about a buffet, a little place up in New England where Jane Austen and Herman Melville go to find topics or themes for their books. And you can read, I've posted the LDA buffet story on my blog. You can go and read it there. And I'm not going to talk about what LDA is. But as a side note, I do want to comment on the notion of popularization, because I think popularizers get a bad rap in the academy. And of course, I can think of some exceptions, writers who were influential in my own youth and maturation, and Stephen Jay Gould, for example, comes to mind. But it does seem to me that many in the academy hold a bias in favor of the arcane and the occult, and perhaps this is why we hide some of the code, I don't know. But back to my point, I think we place too little weight on the importance of communicating these complex ideas. Some years ago, I was talking with a colleague who mentioned another junior colleague who had just won a teaching award. And I said something along the lines of, wow, this is great news. And the colleague said, well, yes, but you know this is the kiss of death in terms of tenure. Well, maybe that example is a bit different from what we're here to talk about today, but I think it is related because I think it highlights the entrenched institutional bias against clarity that exists within some of our institutions, perhaps not all of them. So anyhow, my first point then regarding communication of my own computational research is that I begin by assuming that my audience has little or no technical knowledge. The second thing that I can almost always assume is that my audience is going to be skeptical, and not just about my methods, but about my conclusions, because all of this method in particular is completely foreign to them. Now, this is a very interesting point of irony, that unless you're a humanist, you might miss this point. Because in the humanities, we have a long and honored tradition of reading literature through different lenses. So, for example, we might pick up Moby Dick and interpret it through a Freudian lens, and perhaps even argue that Ahab's lost leg is symbolic of his impotence, and that the whole quest for the whale is some attempt to recapture a lost virility, or perhaps even to slay a father figure who deprived him of his love of Mother Ocean. I'm going off on this. And you think that I'm being silly here in order to make a point, but at least one scholar has written, quote, "Moby Dick is the most extravagant projection of male penis envy in our literature." The irony, of course, is that we, which is to say those of us in literary studies, have a tradition of accepting a wide range of interpretations and understanding that they're interpretations. But the minute that someone brings numbers to the table, all bets are off and objectivity is demanded. The Freudian critic is given a pass. The would-be skeptic replies to the Ahab theory, that's an interesting perspective, but how do you account for the fact that no mother figure in the novel completes the Oedipal triangle? Right. Mention a few numbers or an algorithm, and suddenly a whole bunch of English majors become born-again statisticians demanding hard evidence, if not p-values and confidence intervals. Well, of course, I'm making light of this in the name of pedagogy and to be a bit more entertaining here, but there is some truth to what I'm saying. And the truth, I think, is not that my colleagues are really born-again statisticians, but rather that they assume that the introduction of numbers is a precursor to the assertion of some sort of definite conclusion, a conclusion of a mathematical nature, which is to say an irrefutable argument. And now, ladies and gentlemen, I will prove through the use of computation and arcane statistics that Moby Dick, the whale, not the novel, is God, and by God, I've got the numbers to prove it. This is what they're concerned about. So as I said, my second assumption is that a few in my audience are going to be skeptical, perhaps even hostile to my approach because of this mistaken impression that I'm somehow interested in or intent upon, which is to say with a hidden agenda, undermining the interpretive work that enriches our understanding of literature, and it really is the essence of the humanistic enterprise. So I'm not here to do that, and we're webcasting so I can put it on for the record. Right? I am not, as one of my old colleagues once said when I first met him, oh, you're the guy who's going to take the human out of the humanities. That really happened. Well, to address this misconception regarding my own motivations for bringing computational analysis to the study of literature, I begin with the notion of evidence, because I think that it is something that we all understand, the importance of evidence. And the study of literature relies upon careful observation and the sustained, concentrated reading of text. This is not unlike the sciences, except, of course, the sciences have the methodological advantage of experimentation as a way of testing competing observations. And I think, with some exceptions, there is no obvious corollary to experimentation in literary work. The conclusions that we reach as literary scholars are rarely testable in the way that scientific conclusions are testable, and the conclusions that we reach are rarely repeatable in the way that experiments are repeatable, although there are some cases where they are. We are, I think it's safe to say, highly invested in interpretations, and so it's very difficult to rule out an interpretation. Nevertheless, I think it's also fair to say that science is interested in interpretation. And so my point is that we agree on the importance of evidence, and that evidence then leads to interpretation. And I'm not going to debate the existence or reality of interpretation. I think the important thing is that we need to acknowledge that some interpretations are better than others. Better informed, better derived, or just simply better for being more comprehensive, more reasonable, more believable in the way that they understand and make sense out of the available evidence. So at the time of my Thanksgiving dinner back in the early 90s, gathering literary evidence meant noting things. A phallic symbol here, a biblical reference, a stylistic flourish, and so on. And then interpreting, making sense and arguments out of those observations in order to improve our understanding of a text. But today, in the age of digital libraries and large-scale book digitization projects, the nature of the evidence that's available to us has changed radically. Which is not to say that we should no longer read books looking for things, noting elements, but rather to emphasize that the massive digital corpora offers us unprecedented access to the literary record. And it invites, and I would say even demands, a new type of evidence gathering and a new type of meaning making. The literary scholar of the 21st century can no longer be content with evidence that's gained in an anecdotal way, with random things gathered, even from representative texts. I think we need to strive to understand these things that we find interesting, those elements that we do identify, within the context of a mass of potentially uninteresting material. So to quote the Russian formalist Yuri Tynyanov from 1927, he said, "Strictly speaking, one cannot study literary phenomenon outside of their interrelationships." Unfortunately for Tynyanov in 1927, the multitude of interrelationships far exceeded his ability to process them in any real way. His tools were close and careful reading. Well, like it or not, I think today's literary scholar can no longer risk being just a close reader. The sheer quantity of the available data makes this traditional practice untenable as an exhaustive or definitive means of gathering evidence. Something I think important will inevitably be lost if we ignore the archive. And so the literary researcher needs to embrace largely computational ways of gathering evidence. And just as we would not expect an economist to generate sound theories about the economy by studying one or two consumers, we can't expect literary scholars to do good literary history through a study of a few books. Today's student of literature, again I argue, needs to be as adept at reading and gathering evidence from individual texts as from the archive as a whole. And that means learning something about text mining. And mining here is, to use a phrase we like, the key word in context. I think today's scholars must go beyond mere search. In search, which we're all pretty good at these days, we go out in search of a single nugget, carefully panning in the river of prose to find that gold nugget. Well, at the risk of giving offense to the environmentalist, what's needed now is the literary equivalent of open pit mining. We're proficient at search, we're comfortable searching digital collections for some piece of evidence to suggest or to support an argument, but the sheer amount of data that's available to us today makes search ineffectual as a way of evidence gathering. You have to know in advance what you're searching for. Close reading, digital searching, yes, these things will continue to reveal important nuggets, but I think at the same time, deeper veins will lie buried beneath the gravel. What are required are methods for aggregating that gravel and making sense out of both the nuggets and the tailings, to stick with the mining analogy. And for me, more interesting and more exciting than panning in the river of prose looking for nuggets is the ability to go beyond the pan and exploit the trommel of computation, to process, to condense, to deform, to analyze those deeper strata. To unearth for the first time, I believe, what these corpora really do contain. Now, in practical terms, this means we have to evolve as scholars to embrace a variety of new approaches and new methods that are designed for accessing and leveraging the electronic texts that make up the 21st century digital archive. So now to reiterate, my first point was that I begin by assuming that my audience knows very little in terms of technical matters or statistics. And to address this potential problem, I devote a good deal of time to explanation. My second point is that I must assume my audience is going to be skeptical, perhaps even hostile, but that skepticism is based on a mistaken impression about my objectives. And to address this problem, then, I focus on computation as a means of evidence gathering, and thus my mining digression. So my third and final point regarding how I communicate this research is an extension of the skepticism problem. And it involves what my colleague Franco Moretti calls the so what question. Well, let's assume that I'm successful in communicating and convincing my colleagues that this computational text mining work really is another way of observing and gathering evidence. I must still then address the so what question and demonstrate why and how this kind of computationally driven research is worth doing in the first place. How can I convince my literary colleagues to learn R? Not that that's quite my objective, but that would be lovely. In literary studies, for example, we do not have a tradition that places very much value on the notion of confirmation. Several years ago, I presented some computational work that compared the stylistic signal of Moby Dick to the signals of 3,500 other 19th century novels. And Moby Dick showed up in this work as a statistical outlier with a style that was rather unique within this whole ecosystem of the 19th century novel. Here it is represented in a network diagram. The other dark blue are just other books by Melville, but Moby Dick's the real outsider there. So a colleague raised his hand during this talk and he said, well, sure, yes, but we already knew that Moby Dick was an odd book. And my reply then was to argue that we suspected as much, but we did not really know it in the way that we know it now, which is to say that my analysis brought new evidence to the question. And I think if this were global warming that we were talking about, and not literature, I think such evidence would be welcomed. And I think we could agree that the new evidence constituted a form of new knowledge. So that is one way to address the so what question. But confirmation, or for that matter, contradiction, which is another way that this work finds its way into papers, confirmation or contradiction of existing theories is still only half the picture. New knowledge may indeed be truly new. And here, I think, is where some of the most difficult communication takes place, because it is here that methodology and results are so intimately connected. Without a clear understanding of the methods, of the tools, then the conclusions can be difficult to comprehend because they are so foreign. And here I'm reminded of something that Tim Lenoir, the historian of science, said some years ago. He said that quarks would not exist were it not for the particle accelerators that were built to identify them, to detect them. And Lenoir was actually channeling something that Ian Hacking had said about electrons being real when you can spray them. In other words, to bring this to the home of my literary colleagues, as Hamlet would say, there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Well, in my own work, I'm interested in scale and in how moving from close reading to even one or even several hundred books to a computational analysis of several thousand can provide a way of seeing things that we have never seen before. This approach of mine I call macroanalysis, and it is in some ways akin to economics, or more specifically to macroeconomics. We might think about our traditional interpretive practice of close reading as corresponding to microeconomics, whereas this approach I'm arguing for, this distant approach, is like macroeconomics. The results of a macroscopic investigation is contextualization on an unprecedented scale. The underlying assumption is that by exploring the literary record written large, we will better understand the context in which Moby Dick exists alongside all those other 3,500 novels. A macroanalytic approach helps us to see the operations of the entire literary economy, to better understand the degree to which literature and the individual authors who manufacture that literature respond to and react to literary and cultural change across time, depending upon author gender, nationality, and so on. And so, like those quarks that were made visible by the particle accelerator, macroanalysis provides us a way of discovering new things about literary history. The scale alters our perspective and brings into our field of view that which was otherwise latent or hitherto invisible. What is revealed is neither better nor worse than what we have been able to analyze in the past, but it is most certainly new and is most certainly worth making sense out of, which is to say, studying and interpreting. Thank you.
Thank you, Matt. And I'll ask Dan, our final speaker, to come up and talk to us.
Okay, so thank you for the opportunity and invitation to talk here. I'm Dan Ellis. I'm a professor in the electrical engineering department here at Columbia. And I haven't ever spoken on this topic explicitly before. I think I'm here as a kind of an example of mainstream computational research, someone who practices this and faces the problems of communicating it, and then just some insights from that. And I think I've really enjoyed the talks we had before. I think I'm going to echo quite a lot of what Neil said, but possibly in a slightly more naive way. So I'll talk about what I understand by computational research. When I was thinking about talking, I came up with these 5 different ways of communicating it, which I'll try and contrast. And then I want to talk a little bit about the idea of sharing code as a way of communicating computational research. So I work in signal processing. So it's in electrical engineering, and it's in electrical engineering because the roots of signal processing are in building electronic circuits. But since the 1970s, it's been more or less a purely computational pursuit where people are writing software, writing code to implement the different ideas. And so it's interesting to see how this has changed. And this has changed within my kind of academic career. I started in research in academia in the late 80s. So from the origins of signal processing are in the sort of 1950s, 1960s. And in those days, it would involve building a special computer, right? A special piece of hardware, which is what that picture on the left is supposed to be. If you wanted to access these results, these work, you would have to be someone who was in the lab where this machine was generated. And my bottom point here is trying to communicate the way that the pace of research has changed. So there's a very central algorithm in signal processing is the fast Fourier transform, the FFT. It was actually invented post-1963, but that kind of algorithm might have been something you could think about implementing in those days, but it would have been like a significant piece of work, maybe a month's worth of work. By the time I began doing the stuff in the late 80s, this is a microvax, which is emblematic for people who were around at that time. It was like one of these first sort of mass market, in the research market, generally available computers. It could do a lot for the day. And you could write software on it, and that software you could then share with other researchers in the community, not necessarily an institution. There'd be other people at other universities who also have microvaxes, and you could actually imagine them doing the same kinds of things. To write an FFT routine, which is something I did when I started at grad school, was like a day's worth of work. The algorithm was well established, but you'd have to code it up yourself. Today, I do the similar kind of research on this laptop, using software which is basically freely available. I actually use a for-cost version, but there are these software platforms which anyone can use. And so if I write software, literally anyone, and that importantly includes teenagers in their bedrooms who might happen to be prodigies wanting to work in this area, they can access it. And the algorithm, of course, now is implemented as a single primitive in these environments, so it's like a few seconds to actually to use it rather than coding it. And of course, I could have added more lines along here trying to quantify the changes in capacity and speed, which is sort of in the inverse of the code development. So computational research has changed, and in particular, this means that there's different kinds of problems that we can address now. So there's this computational research paradigm. Generally speaking, you start off with an idea, like I think this is an interesting way of solving a problem. I think this is an interesting way of modeling predicting how the climate is going to change or something like this. But you don't know whether it's going to work or not. Because once we're talking with these kinds of very high power tools, the systems we can build, the machinery we can build is so complex that it's no longer something that you can have a purely theoretical analysis of what's going to happen. People still try and do it, but it's very easy to move beyond the bounds of what's can be analyzed from a theoretical standpoint. In that case, the only choice we have is to actually try it out, to build it and try it and see what we can do. And of course, that's become much easier, so the kinds of things where we can do that have become much broader. Then what happens, right? So then it's like, well, I thought, this technique would work, so I built it and I tried it on some data and I got some results. The results themselves were not something that I could have predicted. That's why I had to build it and run it. So I then have to look at these results and perform some analysis to decide whether it worked, how it worked. And so those things can be comparisons between different approaches with some measure or statistics of what happened to understand what happened. So this is the computational research paradigm, and this is the problem, because now the only thing that happened was the actual results of my software, of my implementation. That's kind of the evidence I'm providing that there's something interesting in this idea. So here's an example from my own lab, which is we have this problem of taking a large archive of videos, like maybe something from YouTube, thousands of videos. We want to be able to find individual videos. There's really no way you can do this except by having some kind of computational mechanism. I want to find all the videos of dogs in this collection. They're unlabeled. They're uploaded as MVI_9377 or something. So, but I have this idea. I know that people are good at recognizing sounds as belonging to a particular class. There's some nice research from psychologists, actually this collaboration with this guy, Josh McDermott, who's in cognitive science at MIT, on how people can recognize sound textures. And he had a set of parameters that he said well predicted whether people were going to recognize these textures. So we implemented these parameters for arbitrary soundtracks, and then we build a machine learning classifier that tries to then rank this large collection of videos, this 200 plus hours of videos, according to those measures. So how do we present these results? Well, this is the current practice. We write a paper. This paper is called Subband Autocorrelation Features for Video Soundtrack Classification. We published it at a signal processing conference, and now everyone knows what we did. In the paper, we included a table here of computation times. This is just to sort of illustrate the complexity that our middle method, the SAI method, took 1,000 hours to compute on this data set because it took a few times longer than real time to process these videos. But here's the results that we've got a bunch of different techniques, and this is some measure of quality, and the new result is better than the previous techniques. It has gives us a larger value. And so now, and this is the academic system working in its intended way, which is people see this, they read the paper, they see the result, then they say, okay, I guess this idea did work, I should now go away and maybe investigate it for myself. However, it is limited. And so this is another thing we did with this particular piece of work, is we made on the web releases of both the code base and the data set. So it's not just you can read the paper, but if you want to, you can go away and you can run this code on this data to get these same results. The code base is around 5,000 lines of Matlab, which was spread over time, a few months of work from me and my graduate students. The database is several gigabytes of data, which is a large database, but something you can distribute on the web quite effectively today. So this brings us to this idea of these 5 different ways of presenting results. Why do we present results at all? Of course, in academic research, we're highly incentivized and motivated to share results. We're doing this because we're interested in knowledge, and we're able to continue our professions because people recognize that we're doing good work. The publish or perish idea, sometimes we are explicitly ranked on paper counts and citation counts, but more to the point, the whole name of the game is impact. You want people to know about your work and recognize its value and hopefully build on it. There's an interesting distinction in publication between math and humanities, where very often writing the paper is the entire product. In math, you have a set of proofs which you're going to publish, and that's kind of it. There's nothing that's not there. In humanities, you have an argument. You're going to, make this very eloquent argument, and that's kind of what you have. In engineering and in general in science, you write a paper about something you did, but there's this whole other hidden part of the iceberg, which is the actual activity. And the paper is more just a report on what happened, but not, not everything that's there. So the 5 ways we have that I come up with are the paper, which we've just talked about already. There's a lot to be said for papers, right? There's a subtext, there's a subcurrent here that we're sort of saying that this is not adequate anymore. I'm saying that. But the nice thing about a paper is you get to present the argument the way you want to present it. So you say, this is what I think is important, this is why, and I can marshal my evidence. But the problem is that it is extremely superficial as a description, say, of a piece of software. So you can give talks like this, and this is now an increasingly popular way of communicating results. The nice thing is you can, it's very accessible, so you can get people in quickly, but by the same token, it tends to be very superficial and can be a distorting way of presenting what really happened. You don't get to discuss the niceties, the finer details. Another way you can present your results is as an interactive demo. So this is a very interesting new development, and again, it's something that's made possible by today's computational infrastructure. So you've got some system, you've got some algorithm, rather than just running the experiment yourself and telling people what happened. You can actually publish something where they can maybe upload their own versions of the data, maybe through the web or something, and they can then, the system will run and then it'll present the results. Now this can normally be it's fairly limited, but it does give the opportunity for people to do their own experiments, to ask their own questions, not just read the answers about the questions that you posed. Unfortunately, this is typically a lot of work, although there are interesting developments to try and provide infrastructure to make this easier, and Victoria has worked on some of that. A fourth method is to actually release libraries or APIs which are deliberately aimed at letting people incorporate them into their own workflow. This is something that Neil mentioned. This is popular this is an interesting trend in startups where a company with some sort of commercial interest will make an API freely available over the web to try and promote interest and understanding of their techniques, even though they're then hoping to monetize in some other way. And so this is an example as a company called the Equalizer that I've had some workings with, who have this open web interface for uploading and analyzing audio. It's a very good way to get people to use your ideas, but again, it does have some liability in terms of the development and support. So the fifth way is code sharing, is simply if you've written some code and that's been the essence of your research, you can publish it online, just as we did for the video analysis, video soundtrack analysis. And the nice thing about this compared to a traditional journal paper or something is that it is, by definition, a complete description of what you did. If the code is something that can run and that can reproduce the results, then any question that someone has about how you did something, it's there. They can go and check the source. The source is the documentation, is one of these sort of little jokes in software. They can actually see what happened. And so the ultimate, we can say what happened in every case. But it also has these interesting secondary advantages, again, as mentioned in Neil's talk, that if there are problems, there's a much better chance these problems, these bugs, are going to get uncovered if people can see exactly what you did and go through every step. The disadvantages, of course, are that it does require some amount of effort to prepare and document. But there are other things. There's this idea that maybe there's something that you're not particularly proud of, that you've sort of glossed over in your paper, which is now going to be exposed and which people might want to focus on. And even if your work is fantastic, there is this idea that maybe you've still got to you've got to think about your future. You've got to make future academic work. There is this idea of competitive edge, and if everyone can now suddenly use your software, they can maybe it's this leg up that you're giving away. So. A few more discussions of issues of code sharing. The scientific mission is to try and advance knowledge and make substantive improvements which we can then build upon. Often in different scientific fields, there's been a struggle to try and develop protocols that will allow reproducibility. So, in chemistry, there's this whole, before we can do chemistry, we have to agree what the standard reagents are, agree ways that we can measure them, agree ways we can describe experiments that we did that allow them to be reproduced. In some social sciences like psychology, this is even harder a problem because there's so many variables. There's a lot of effort has gone into making sure that if I describe an experiment, you can actually reproduce it in your lab. The beautiful thing about computational research and the incredible drop in cost of computation and the way that computers have become commodities is that stuff is almost taken care of. That I can release my Matlab code, and Matlab code is, it's the 2013 equivalent of this, multi-million dollar engineering effort to build some machinery. Now it's just, here it is, I can duplicate it at zero marginal cost, and I can give it to you effectively at no cost, and you can run it. And so that's like this incredible opportunity in terms of reproducibility and sharing of research results. So why don't people do it? Well, these are some results from a survey that Victoria did a few years ago at a big machine learning conference, NIPS, where she asked people, why don't you share your code or your data, and tabulated the results. And the top hits, predictably, are basically, well, it's a lot of work, right? It would take me a lot of time to document and clean up my code to make it releasable. And then even if I did that, I would get a lot of questions, and so suddenly I wouldn't be able to put time into research because I'd be helping people understand my code, or, you know, might feel tempted to try and help them because they would be asking these questions. Some of the other answers were also interesting to me, that there are clearly these ideas that, well, you know, if I give this stuff away, then maybe the benefits that ought to accrue to me will be cut out somehow. But these are, you know, this is empirical evidence. So this is definitely what people are thinking. So what's going to happen in the future? Well, I think that there are, you know, the practice is still developing because this opportunity is novel. That it's, in particular, the increasing development of widespread high-power computers and programming environments that allow people to write very complicated things relatively quickly. This is a new thing, so we're still trying to figure out exactly how it plays out. But there are definite, you know, there's the whole open source movement, which isn't particularly about research, but which is about the opportunities to share that become available with these resources. There are drawbacks to sharing code, basically the time involved in making it available, and maybe the fear that something's going to come out that will, you know, undermine the way you've presented it. But there are huge advantages, and I think this is something that has surprised me in my own experience, that I've, you know, for various reasons published code, and then I've had all these unexpected benefits that, firstly, it was very important in, you know, I believe in me getting tenure, just because it was an extremely effective way of letting people know about my own work and getting some kind of profile within the community. And then, of course, there are advantages to society, not just to the individual, in terms of advancing scientific mission and allowing reproducibility. So to summarize, computational research is different from other kinds of research, partly because we're able to build things which are much more complex than we would typically have had the time or opportunity to build in the past, which is a great thing, because now we can build these models of, you know, climate, what's going to happen in the climate, which, you know, you couldn't just build from a single, you know, you couldn't work out on paper. But it does mean that there are these problems, that these things are sort of beyond the comprehension of individuals and can only be understood empirically through what they do. Traditional publication is not really adequate to fully describe this, although it still has a very important role in terms of giving you the opportunity to try and abstract out and say what really mattered about this work, what the important parts were. But I think that it has to be very much done in tandem with code sharing. That code sharing has, you know, this sort of slogan from the open source community that if I can't fix it, if I can't change something, I don't own it. And so we have to, by sharing things, we do allow people, we give ownership of these ideas to the full research community, even at the cost of exposing some of our dirty laundry. I think that what's going to happen is, again, as Neil mentioned, there's going to be a generational change. People's attitudes to sharing will change, and people's maybe anxieties about, you know, the quality of their own code will become dissipated as it becomes more widespread and everyone understands that we're all in it together. All right, thank you.
To perhaps take a seat at the front, and we can entertain questions. Great. Well, I certainly have a few questions myself, but before I exert moderator's prerogative, if there's anyone who in the audience who has a question, perhaps they could step up and we'll kick off the discussion.
Hi, I'm Alex. I'm the Digital Scholarship Coordinator here at Columbia, and I have a question there's a tension that I heard between sort of the need to allow reproducibility and sharing, and the need to popularize. I couldn't help but hearing a small disconnect between the two, where the one actually hides the code they weren't sharing. Is the way to go just to do both, and then now look, more work now? You guys have to say about that.
Let's take this first. I guess I'll make a comment on that. I think you may be right for some of that, because I think the movement to popularize and to make things understandable does potentially hit you, as particularly as you mentioned in your talk there at the end, because it detracts from the work you have to put in to make things reproducible. But I don't necessarily think that sharing or the lack of sharing is a problem when you are trying to popularize. Indeed, I think it's the other way around. I think by sharing you do popularize. It's one of the mechanisms that you can make things more understandable and more communicable. But there is this elephant in the room that's been brought up very vividly there, which is the thing that most people worry about is how much extra time is it going to take me? And I think the only thing that we can really do to challenge that is understand what is it that you get out of it at the end. So is the extra time up front worth it in terms of the work you have to do at later stages? And indeed, a lot of the things that we've seen about sharing code is that the benefit you have to realize isn't about making it necessarily easier for everyone in the world to see your stuff. It's about making it easier for you yourself and your close colleagues to reuse and to automate, because that's the sort of impact that really does have an effect on you. If you can do your own research faster and at no extra cost help others to see and look inside, that's a benefit to you primarily, and you get the sharing for free.
I don't have anything to add.
Okay, I think this is a really interesting question. It was something I didn't put in my about the idea of the tension or the contrast between sharing code and maybe providing interpretation, providing making what happened accessible. And I was looking at Matt because I think his slide about the LDA buffet, right, is exactly that. It's like the kind of thing that makes me, as someone who teaches mathematics behind something, teaches something by using mathematics, right? There's always this kind of like flinch when it's like, oh, here I can explain this with this analogy, and it's like, yeah, but don't use the analogy, use the actual math, right? Because that's somehow a purer answer. But at the same time, I absolutely believe that if all you've got is a piece of math and you don't have any kind of intuition of what's going on, then that to me is not, you haven't understood it. You may be able to exactly describe it, but you haven't understood it. And so there's this interesting angle, which is, well, if I give you the code for something, it's like, I don't have to say anything else. Here is my description. It's complete, it's exact. This is what it does. But am I going to then use that as an excuse not to actually talk about what's going on, what the ideas were, and what's happening inside? And so I think there's a weird kind of danger that as code sharing becomes more commonplace and more routine, that maybe it could take some of the pressure off other kinds of explanation, just because, like, well, it's already as perfectly described as it could be. And I think we need to avoid that. And so I think that it's more than just sharing code. You will still have to try and provide as much interpretation and structure and do your work to explain your work.
Can I ask you a follow-up question, Dan? One comment that sometimes gets made, and you started talking about it a little bit in your slides, which is when you said that the proof is in the pudding.
Yeah.
So if I have a piece of software, and maybe it's a black box, and I can take what I'll call an engineering approach to it, which is, well, I've applied it to test data sets and original data sets, and it just works beautifully. So isn't that enough? So in a sense, I can test the code in certain ways, but I don't really need to get into the guts of it because I've just shown you that it works well. And so I wanted to hear your thoughts on that, as well as I think that also leads to another question, which is, well, my code base is massive. Even if I shared it, people can't really realistically read it. It will take them years. So then what do I do? Is that kind of testing that I just described, because it's effectively a black box in that sense, is that testing enough, or are there other approaches I should be taking? And I think this is you could perhaps characterize this as a tension between science and engineering. Does it work, or what are your methods, and how are you communicating them?
Yeah, I think that's another good point, that where I am advocating, and there are many people advocating, open source release, because it's this idea that, well, now we can see exactly what you did. And anyone who's actually written software understands that that is not a given. You can write software and you can make it very difficult to understand what you did, or you can write it in a way that makes it very clear. And so it's interesting that now we're getting more towards recognizing software as a means of expression, not just a machinery, a technology, but actually as something with aesthetic qualities. Any programmer would not consider that to be a crazy thing to suggest. And so then there's this interesting angle that, well, okay, here's this code base that works, and here's my program, and it kind of does the same thing, and maybe it doesn't even work quite as well. But now I can say, but you can look at this and you can understand what's going on, and maybe you can reuse it or adapt it, whereas this thing is completely opaque. Right. And that there's a market for that, there's an angle for that. And I've had a sort of a minor career in taking well-known algorithms, recoding them in Matlab, and getting the credit for having done that.
Yes.
Hi, Rob Cardellano from Columbia Libraries Information Services. Are there disciplines where code sharing has become more of a norm as opposed to something new and accepted? And is that, do those disciplines serve as exemplars or perhaps ways to influence some of the other academic and scientific disciplines?
Do you want to?
That's a very good question. And I think it's still something where, even in the areas where you do see increased sharing, that it's still in its infancy. So there are some areas where you can see the code, particularly smaller fragments, being shared more commonly. If you look, for instance, R was mentioned as an example of a platform that many people use. So you use R. It's interesting to see that there are projects such as the Open Science project, where a number of routines are being created and shared openly, particularly for things such as bioinformatics, whereby you can see the code itself, you can see test data sets, and you can see papers that have been produced using this code. And I think there you're starting to see this change between large monolithic programs and this idea of modifiable pipelines. So in one sense, one of the questions that you brought up there was, if you've got all of these massive thousands, hundreds of thousands lines of code, how can you ever inspect it all? And instead, by breaking up the problem into much smaller chunks, what you're doing is trying to increase the trust level in terms of at least some people will have viewed each individual chunk themselves. So I would say that in the areas of particularly the computational life sciences, this is very much changing. And that's interesting because that's also one of the areas where there is the most commercial interest. So one of the levelers that open source in particular gives is actually enhancing the ability of doing academic and commercial collaborations, because a side effect of open source licensing is that it becomes possible to do work with a group before you've signed an NDA, or without having to have signed an NDA. And I think this is more a side effect rather than what it was intended for. But it does open up a whole new model of collaboration, commercial collaboration.
I'll add something to your comment, Neil, which is, so you mentioned R and people who are working in R and sharing in R. Statisticians, generally speaking, work in R as well, and there's a understood and widely used repository at our CRAN where people will put packages and so on in there. So my understanding in statistics is that's a pretty normal thing to do, and in a way you would expect that, because as statisticians we're developing methods. Oftentimes we'll have an implementation in code, we're trying them out on data, but we have taken that extra step to put it in a repository. But like Neil said, this is also an example where the sharing is still in its infancy. It's shared like an open source package where you have, it's not necessarily tied to publications or tied to reproducibility, but this notion of getting the code out there is there in statistics, for example. Yeah, please take the mic if you can.
Dennis Tan in English department and data sciences and other things. It's not really a question, I'm just thinking out loud, is that what struck me about, so several people said that it's more effort to publish code. And to me that, I think even more radically than this is that, like if somebody said, it's more effort to explain what I did, or it's more effort to publish my figures, you would say, well, that's ridiculous. Of course, we just expect you to, as part of this genre of the scientific article or scholarly article, to just expose your methodology. So it seems like we can pose this question slightly more radically, where we can demand to see the methodology in kind of a more robust way. So that's one. The second thing, and that's something that we've been talking a lot about kind of in the humanities side, and it's a bit of a problem, is that we are, in a way, in the humanities in kind of the very beginning stages of thinking in this way and thinking about sharing code and writing things. And in many cases, we don't quite have, right now, the shared standards. So somebody is using R, somebody is using Python, somebody is using some black box tools. And I'm not quite sure at this point where, whether we have the expertise in the community to kind of cogently kind of evaluate our methods. So part of this is and I look at the statistic community, for example, with some envy, where they have kind of banded around a set of tools, more or less a toolkit that they all share. So I'm wondering whether Matt and others could address this question of common standards, the importance of adopting a common set of methodologies and tools.
I'll take a stab at a couple of comments that are going to be more of a confessional nature. But all of this sharing of code is great ideologically and so on. And then I think about, in practice, what that would mean for me. And I got started in R back when the R user community was not nearly what it is today. And it was a cruel user community at that time for a humanist with not really any deep stats chops to be posting stuff to the mailing list. Now we've got Stack Exchange and all these fantastic things where you can get great help. But maybe because of those experiences, I've become extremely nervous about posting extended pieces of code, not so much because I'm worried that a mistake will be identified. I'm not so worried about that, but the matter of elegance came up a minute ago. Mm-hmm. And I can assure you that in my code there are probably on every line an alternate way of doing something that would be more elegant or more efficient. And I don't really worry about that because my interest is in getting an answer to a literary question and not so much with producing an elegant piece of code. And in fact, there's no reward in my field for producing an elegant bit of code. So there's no incentive really for me to do that. So I would love to do it on the one hand. To do it would require a massive amount of work. Writing up the LDA buffet thing, I mean, that took 2 days of my my scholarly time to write that up. I like it, I think it's good, but it's not going to get me tenure. Not that that's all there is to a career, but I'm just, we don't have the system of incentives for a lot of this sort of work.
I'll throw in a quick story. I was once told by a prominent computer scientist that when I asked him why he wasn't this was a number of years ago, why he wasn't putting his code out there, he goes, I can't share my code. I'm a computer scientist. Mm-hmm. Idea being there would be certain standards in the computer science community, and you probably wouldn't sort of meet these standards of elegance.
Yeah. I think you made a very astute observation there, though, that you could just ask the question, isn't it just too much effort to publish a paper? It's a lot of effort to publish a paper. That's what I use to blame the fact that I don't publish enough papers. But ultimately, I think it comes down to, as you've indicated, the question of what's your incentive for spending effort. And I think there's another thing that you brought up there, which is the reason why, well, in some ways it's not your job to make your code elegant. But the question is there a role there for someone else to make your code elegant? And the answer is probably yes, and they could do it. But there's no incentive for them to do it because neither they nor you get any sort of real kudos for having done so. So I think the problem we have is symptomatic of the fact that the way that we treat the work that people put into things is skewed. And so the reason why, for instance, we have the same question about do we get a loss of competitive edge, we shouldn't have to have any question about whether you lose competitive edge if we had a system that rewarded you for your work being reused. But currently the only real way that you get rewarded for your work being reused is if you have a patent, or perhaps if you get your publication that describes that work is cited. So there's an issue there, and that's, I think, one part of your question. The other thing that you said was about standards. So do shared standards help? And are there things where you can see communities coming together to make it easier for people to exchange work? I certainly think that shared standards do help. Although one of the caveats is that for a long time I was involved in the standards community, and the issue was that they were trying to standardize things for which there was no real interest in sharing information. So I believe very strongly in standardization where people need to come together and collaborate. But there is this movement that suggests we should standardize everything. I think I'm a bit more pragmatic than that. Where is it that we need to come together and share information? That's where we need the standards. There's no reason why some people can't work in Python, some people working in R. But for instance, in terms of doing text encoding, it's useful to have a standard in doing text encoding so that you can share and you can develop software in any language that allows you to work with that.
There was one thing I wanted to add. I'm interested in the ways that people sometimes, systems can help people overcome limitations in their own motivations. So you write papers because you understand that that's how it's being imposed on you. But there is this common experience that when you actually are forced to explain something or teach something to someone, your own understanding improves. That suddenly just the exercise of trying to explain it out point by point can improve your own understanding in a way you didn't expect. And this is very true in coding, and I think Neil mentioned this, that actually the exercise, the practice of going through and cleaning up your code so that you're no longer ashamed of releasing it into the world, very often you actually fix things when you're doing that. It's like, oh my God, I didn't ever look at this because it wasn't something I had to look at, and now I discover these problems. And there are all kinds of unexpected benefits to sharing, which maybe we need a few incentives, external incentives, to help people do the right thing, which they'll thank us for later.
But maybe some of that incentive is purely personal. There's someone that has posted something on Refactoring Fridays, which is the same idea that you might have of at the end of a week you kind of clear up your desk, you look through your task list, you understand what things can be changed, what things can be reprioritized, what things have become irrelevant. And doing the same thing for your software. So every Friday, setting aside a little bit of time to look through what you've written, assessing what's still important, what you don't care about, and so on. And this is someone coming from the remote sensor community, so it's coming from the geosciences, but I think it applies very readily. It's what can I do that makes my life easier, rather than necessarily having this altruistic view of being perfectly accessible to everyone, because ultimately, until the credit system changes, you really want to be putting in the effort where it will help you.
Okay, well, I have a question for Matt, actually. So if I'm understanding you correctly, I can see two places where reproducibility might intersect with what you're describing. There's this notion of reproducibility. If I've been able to do something like produce the Moby Dick network map with 3,500 novels and so on, where I might want to verify that and look at the code you used to do that so I can get my hands on your R scripts and go ahead and regenerate it. I think there's another way that reproducibility can be interpreted in the context you're describing, and not being from the humanities, I'm less familiar, so maybe you'll just end up correcting me. But this notion of building your research, the evidence is based in particular texts. And so what I might want to do when I'm evaluating the work that you've, or the arguments that you're making about a particular interpretation or a conclusion, I might want to actually like kind of go back and look at those original snippets of text or whatever you're calling your evidence and so on. And so in that sense, there's another dimension of reproducibility in the work that you're doing. So how can that be facilitated? Are there new models of citation, perhaps, that are being developed around this, like how I actually cite or reference those works, or hot linking or whatnot? Is this dimension of reproducibility, or is this just something that's just taken care of and humanities folks have already thought about it and it doesn't even matter?
I'm not even sure I know how to answer the question quite, but the thing that keeps bouncing up in my head is that we've got another big problem that I didn't mention, and that's copyright. And that much of this work that I've mined is half of the corpus is a proprietary corpus, that so I can't release my data along with my with my code. What I can release, however, is the derivative data. So word frequency counts or something similar to what Google has in the Ngrams viewer tool, right? I haven't done that yet, by the way, but even that, it seems, is being challenged in certain court cases and so on. As far as the other piece of your question, I'm not quite sure I get what you're moving me towards there.
Okay, well, I'll take a stab at clarity. Maybe I'm not really moving you towards anything, but my idea is, how do I really get into the original piece of literature? Forget copyright for a moment. Suppose it's all accessible to me. How do I get into the right place in the original piece of literature? And that's something where traditionally, in my understanding, humanities they'll cite pages or whatever it is. But it seems with the technological developments, that's part of sort of reproducing the thinking of the original author, being able to get back into those original texts in the right way. So, immediately hot linking comes to mind, but it seems that component somehow has to tie into what you're doing in your work, because that, in my non-humanities mind, seems to be part of this issue of reproducibility in the humanities that may be distinct from the sciences.
I get what you're asking now, and there are folks who have developed platforms for doing precisely this. Okay. And we did a bit of this through a Mellon-funded grant in a project called Caesar, the software environment for the advancement of scholarly research, I think is the acronym, but built a system that was doing some of the same kind of text mining applications that I'm showing here, but then allowing you to drill back and, for example, identify which are the texts that have the most of this particular feature in them, and then which place in the text has that, so that you could then have a page citation. That, of course, all has to be firewalled for the copyright purposes.
Yeah, I'd like to suggest to the Scholarly Communications program that maybe next year we do a deep dive into these copyright issues. It could be a fascinating session, especially around fair use for research and education. Okay, I have one last question, which was for Neil. So you mentioned in your talk, with your emphasis on complexity, these sort of very large-scale scientific models, like, for example, the climate model with incorporating airflow or economic components and all these kind of, probably those are some of the biggest models that we have in science today. And my question is, I'm wondering how you can translate those conclusions to what generally gets called sort of the long tail of science, where you have someone doing, say, single author work, a psychologist does a survey and analyzes, which is just as much computational science, and he or she may have scripts, maybe not as massive code bases around the models, but just as much in terms of scripts and data to share, and he or she is facing these very similar issues in that particular context. So do you see a relationship between those different scales of research, or maybe even these smaller scales might be directly linked and feeding in? I mean, I don't know if psychology is a good example, but I can imagine some future where these larger models are incorporating these sort of smaller efforts that are coming out of the long tail.
Indeed, it's a very good point, because I think one of the things that's become particularly prevalent in things like social sciences is this idea where you have data fusion or augmented research, whereby you have standard bodies of work and standard models to which individual researchers can start asking questions and drawing additional conclusions from. And this is kind of going into the long tail, the individual researchers. And part of that has been both the publication of these models and systems, the publication of the data, and making them available through APIs. So talking about particularly some of the work on the mixed climate coupled models, there was a project that was sponsored by the Worldwide Fund for Nature called Climascope, which was to provide a public general scientist's viewpoint onto what is quite a complicated set of different economic and other models for policy makers. So the idea here is that climate change policy makers have at their fingertips a number of different models, and they have certain tools which are made available to them, in particular from the Tyndall Centre at University of East Anglia, that help them make decisions. So that is in itself already a simplification of different coupled models. So the next stage there is to provide this interface in a better described, even more simplified way to the general scientist to see where they might choose to take their research next. So the question is, amongst all of this long tail of scientists, there are going to be people there who have this bright notion of, okay, so they're doing this, but how does it affect this particular thing that I'm interested in? So for instance, is there a link between my research in terms of prevalence of skin cancer with the aerosol model that I saw? And I think that's where it's really interesting. The other thing is that this is coming up in the sort of medical sciences, where there are a lot more individual affiliated researchers, but there the issue of what it means to share is a little bit tricky. So we talk about sharing the large systems, which is fine, but then how do they share back? Because often they do not have the infrastructure. They're not affiliated with a large-scale university institution. The hospital institution, particularly in the UK where I work, does not have the infrastructure to allow sharing. Indeed, it's dead set against sharing. The clinical medical community in the UK is very, very closed, and there are a lot of restrictions on what you can do, even if you were to be affiliated with a hospital which has the resources to do it. So it's going to be a challenge, but I think that the long tail of science is the place that's asking the interesting questions. And if I may go on a little bit further, one of the things that hasn't come up as yet in the discussion, which I think is really important, is the idea of computational research education at the schools level and at the undergraduate level, because I always believe that one of the biggest ways of testing the accessibility of your research is finding out whether or not a high school child can ask you a sensible question about it. So given that we're meant to be making work accessible and making computational research accessible, how do we do it to enthrall and infuse the next generation of researchers in every area? And I think it's really interesting because you've got code.org that's been recently announced looking at teaching people how to write software. You've had similar initiatives in the UK. We've had something called the Raspberry Pi, which I believe has gone quite viral, looking at reincarnating something that I was part of. So about 25 years ago, the BBC decided that it was going to teach people how to develop software. It went out to hardware manufacturers, said, give us machines for schools. It came up with a TV program that popularized it. It was no longer a niche concern. It was mainstream science. And I think this is another shift. We've realized we've lost a couple of generations. But, yeah, I know, it's kind of scary, but we have. Probably my generation. But it's this idea of taking it into the mainstream again. There should be no reason why programming is considered geeky. Well, it should be considered specialist, but not geeky, or kind of somehow the wrong thing to do. Why should it be? It's like being interested in the movies, or like playing sports. It's something that some people will be better at, and some people will be worse at, but it's not something that you shouldn't do.
So, other questions? I have a final question for the panel, and I'll start with Neil if I can. One thing that so I'll throw out possibly a straw man argument. So if we have this situation where the code behind these results is easily accessible, and perhaps even built into these pipelines towards specific results, are we losing our intellectual independence in a sense? And what I mean by that is software is hard to write. And if there is, it's very brittle, breaks easily, and if there's a function or like a coded function that does what you want it to do, is there sort of a sense to kind of maybe lean on this rather than rewrite something from your own sort of interpretation that may or may not be the same? And so I wonder whether we are building in a system where there's a type of intellectual lock-in for solutions for certain problems, particularly as we develop very complicated systems that are hard to just kind of take a new approach and rewrite. And I wonder about that versus a situation where the code is not generally shared, and if you want to contribute, you're probably building from scratch.
You've been thinking long and hard about this question. It's a tough one. I would counter that by asking whether or not you think in general there is an intellectual lock-in these days. Because I think we are in the situation that in many disciplines and domains, we already have some of this intellectual lock-in because we concentrate on our own areas and take on trust other pieces of contributed research. And we're not expected to necessarily go into those pieces of research and reconduct them ourselves, because going through the process of peer review has encouraged us to be able to understand that these things are valid building blocks. And so I think there's a distinction to be made as to whether or not it is something which you are taking as something that is already part of the sort of research literature, or whether it is a new area where you and a number of other people are competing to understand how best to implement a new algorithm or understand a new approach or a new paradigm. And it varies there, because I would say that for the former, it is no different. We have this intellectual lock-in, and I think it's a good thing. It means that once you understand how to do things from first principles, you don't have to do it again.
Right.
In the other area, there is still the open question as to whether or not, where you are striving for the leading edge new discovery, whether it's better to share or whether it's better to keep closed. And that's one that's been brought out, for instance, in areas such as the sort of genome coding projects. And I'm going to leave that one open because I don't think the jury's in on that one yet.
There are other comments.
I'm going to pass.
I just think, I mean, I was thinking about this too, that there's this really interesting, tension between using the second best thing because it has, like the sources available and this, versus using the best thing, which is maybe, for cost, and what are the dangers that somebody is like, gee, my system, my approach isn't very good, no one's going to use it, but if I give it away, then maybe I can get it used, and is that somehow distorting the intellectual landscape? But I think there's this interesting thing that if there is something which is good but not available, it's always sitting there as this target for some brilliant teenager who's going to come along and implement it for free. Yeah. And so that sort of works quite well for us.
I'm just struck by this. I wonder if some of these questions you're raising have been solved by some parts of the open source community or the computer science community, but as Matthew mentioned earlier, sometimes those communities can be, although they're open in spirit, sometimes they can be closed in who they welcome in to their communities because of traditions or other types of cultural impediments. But some of these things that you're asking sound like they've been solved in some parts of our open source world, and maybe that's an area that requires some exploration and interdisciplinary collaboration at a different level.
Any comments?
Yeah. Indeed. I think particularly this idea of a transparent and open collaborative process, which admittedly does not happen in many open source projects. So I make the distinction between open source as a license and open collaborative development as a process. There are many things that translate, but in some sense we've got to this point which is really odd, in that this has happened for centuries of research, that we've both had this conflict between people who research in a collaborative nature. You see the Royal Society being founded as a way of trying to share knowledge and increase collective competition, I guess, and people who prefer to pursue the individualistic path. And I think we do have lessons to be learned from the open source community, but I often wonder whether it wasn't the case that the open source community looked back and picked the best examples of things before. So I think it's this constant cycle of improvement.
Yeah, I want to follow that one by asking if at all anybody has explored the ways in which institutional collaboration can help get the ball moving along. So we talk about that extra layer of work, right? But if it becomes distributed work through different resources we have at the university, collaborations between IT libraries and departments at different levels, and between research assistants and yourselves, whether this enterprise all of a sudden can become more doable and more we can arrive at Shangri-La quicker, rather than other than perhaps imposing it from the top and there's a mandate, everybody will do it, or waiting for this generation to decide they're going to reward us with tenure and promotion for these things.
I guess I'd put in one note here that this is something that's new to us, certainly, and I won't use the humanities broadly. Literary studies for sure, though. The idea of collaboration in general is a new idea. We had some really good success moving in this direction at Stanford in developing the literary lab and really bringing together a group of people working on a similar questions. One of the things, though, I was thinking as the talks were going on today about the importance of sharing code and so on, I was thinking, I'll bet you, though, that these guys have a whole lab full of graduate students who can help polish that code and get it ready before it goes out the door, where, for me, it's completely a solitary endeavor to do that. So anyhow, that was a little bit around the question, but we had some of that collaboration also at the institutional level at Stanford through the Academic Technology Specialist Program, folks from the library working in support of faculty projects and that sort of thing. So I think that's maybe what you're driving at.
Yeah, specifically, I know that at least at the library we run a GitHub repository, but it's a GitHub repository for us. But then I'm thinking, what would happen if we would start having this GitHub repositories for, say, departments? Just I'm throwing that out there, and then we would have somebody working on that, and that person actually could be the one also trying to help out and clean the code. Just one staff line for these things. Go ahead.
Yeah, this is something we've been looking at a lot in the UK because we've come to realize that most of research is about bringing the right people together to exchange ideas, and you have specialists, and it's more so, I think, in the sciences than it is necessarily in the humanities. But certainly most of science now, research is conducted in teams in a lab where you have different specialisms. You'll have your PI who brings the team together. It's the director of a film, if you were to use that metaphor. And then you have the cameramen, the script writers, the people who run the cables, the people who bring along the tea and coffee. So in that same sense, scientific research has become about making sure you have the person who is the experimentalist, understands the statistics, is the computing specialist. Now, one of the things that we've been looking at is understanding where should those computing specialists sit to be most efficient. So some of the larger scientific consortium, for instance, in particle physics, in astronomy, will cite those specialists within a consortium and make them available to the group as a whole. And that's possible because those consortia are large enough. And that's a really interesting approach because it means that there is someone there to clean up the code and make it available to be released to the outside community. Other people, UCL have just started this, have said the right model here is to create a group of people, in this case 4 people who are based at the institution, whose job is to go out and have coffee with people all across the institution and understand whether there is code to be cleaned up. I think we're still too early to understand which is the right way of doing it, but we probably are far enough along to understand that we do need people like this. It's just the question of how do you pay for them? Mm-hmm. And it's like anything. It's like saying, why should you have an educational technologist? Why should you have a subject librarian? We sort of can give anecdotal evidence about why these people are good? Can we give harder evidence?
There are some interesting non-obvious things about why people do research, right? Why people go into academia. And certainly I'm thinking about the graduates, my own experience and the experience of people in my labs. The thing I'm thinking about is some people get into this because they enjoy the programming part, right? That actually it's the particularly in engineering, the pleasure in building is an end in itself. And then you end up working on some project because it involves a lot of that, not necessarily because you're primarily motivated by what's going to come out of the project at the end. And so in that respect, the idea that, like, don't worry about the programming, we'll give you these resources, we'll give you these programmers, and you can be freed of that, isn't quite as easy a sell as it might appear. Having said that, I've worked in some of the, not in my current group, but in some of the other groups I've worked in, there have been people who have become that, right? People who maybe started off in the research track, but then became, staff scientists whose job was basically software support. Because if you're doing it just because you kind of like doing it, but as an amateur, then there are definite limitations, and there are times at which, like, this code is no longer interesting to me, and but now it's central to the mission. So you have someone who can work on that, and that is a really useful thing to have, very powerful setup. But it's very difficult to impose. It has to. These things have always emerged sort of informally and organically, and it's difficult to imagine it working any other way for me.
Okay, so if there aren't other questions, I'll actually give an opportunity to the panelists who may want to ask a question to each other. So if there was anything that you wanted to pose based on the talks that you heard or whatnot, I wanted to give you an opportunity to go ahead and do that.
So I had a question for you, actually. In listening to your talk, I was wondering, in terms of the thing that you put forward about people feeling that as soon as you introduced mathematics or statistics or something, that they had to somehow shift their notions of what your research method was. Is this because you feel that they themselves feel inadequate in their ability to challenge it? Is it because of a fear of not understanding that people push back on this and become much more hardline? Or was it some other reason?
I hate to generalize. It makes for a good talk, but of course there's subtleties to. I think for some it's a knee-jerk kind of. Many in the humanities have self-selected into that field because of a dislike of mathematics and so on. So bringing that in can seem very challenging. But I don't know if there's a simple answer to that. And it's certainly not the sort of thing that you see all the time. As I mentioned, I tend to run in a crowd that's more accepting of this sort of thing. It's when you present it at a more traditional forum where sometimes it engenders that response. But I can't say there's one particular thing I could go after.
Thanks.
I had a question for the more scientifically minded, and that's just how does code get recognized in your tenure and promotion kind of practices? If you put code out there, is that considered a scholarly product?
Yeah, people are definitely trying to push towards that, so that they'll, there was recently a change in the way that the NSF, the National Science Foundation, stipulates that you describe you have to produce a 2-page CV in your proposal, and it has to be in a specified format. And it used to be list 5 major publications, and now it's list 5 major publications or products. So that they're saying, okay, it's okay to put something which isn't a publication, but which is something like a piece of software. So there's a recognition that that's important, and people are trying to move it, but it's a slow process, and it doesn't work very well. However, like I said, I feel like it worked for me, and it was purely informal. It was just that by doing these things, people knew about me because they were looking for their grad student was looking for implementation of something. They found it on my website, and they mentioned that, and that somehow word got through that I got name recognition. And it's more for me. It's always been surprised to me at how it's worked much better than you might expect.
And I think just to reinforce that, so in the UK we have this thing called the Research Excellence Framework, by which university research groups are judged. And indeed, a reasonably significant proportion of the funding, approximately 20% of all universities' funding, is based on this. And in the latest guidelines that are being implemented for the 2014 exercise, software appears across all of the different subject panels. So it's something that you, along with data sets and models, that you can now add and say, this is something that I want to include in my record. The issue still is, though, that whilst it's allowable, how do we judge it? So this is always judged as being, is your work internationally leading, internationally outstanding, nationally leading, so on. And our problem really is understanding how we judge software when there hasn't really been any track record of judging software on these panels. So I guess it's back to what you've said. If you can get your name out there and associate it with a well-known, popular, well-used piece of code, you have a much better chance of a panel being able to take a look at what you've just put in your CV or in your ref return and say, actually, I've heard of this. This must be an indicator of someone who's done good work. So, yeah.
But I think it's so funny that we have this whole system of publication and review and stuff, and it's like, oh, it's a very strange, arbitrary thing that we do. And so people learn how to work through it. It's like, okay, I get the reviewer comments back, I'll do what they say. But at the end of the day, we're not writing papers because we want to get them into journals, or we shouldn't be. We're writing papers because we want to share our ideas. We want to get ideas out. And there's a huge, you shouldn't be the reviewers you're worrying about. It should be the readers who you want to actually, appreciate the value of what you're doing. And the software is the same way. That, we have this problem now that there is no equivalent of the peer review for software. So it's like, oh, I produce this software, and it could be garbage or it could be really useful, and you can't tell just by counting it. But if you can at least track use and however informally, then that's the real test.
And it's starting to change. I think it's Biostatistics. The journal has produced guidelines for how you review the software. So it's
really interesting.
We're at this tipping point. It's really interesting.
Yeah, so to add to that, I think we are at this unstable point where publishing computational results that essentially can't be verified, and you do need the software and underlying data to verify this, is a change that's coming. And so this is something, the tenure committees and promotion committees are made of people who are becoming more aware of this issue. So that's one of the things where a discussion like this can have a corollary impact in sort of informing and raising the issue. And in my experience, this is something where people are becoming much more aware of this. Even if you don't see the formal standards at journals or with funding agencies and so on, informally, I think a candidate who is sort of producing scientific results in the old model, it's very noticeable when they seem to be just completely innocent of these issues around verification of their results and reproducibility of their results, and I believe committees are noticing this. So there's also this sort of very human change that's happening. Okay, so I think we are very close to time here, so I think it's probably a good idea to wrap up and thank our panelists.